It's a great pleasure to be here and to tell a little bit more about what we did in terms of weak supervision. Before I start, as Michael said, I'm currently a postdoc at EPFL in Switzerland, and just a little bit of slides on what our lab, the ECEO lab, is about. So, as he said, we're doing environmental computation, we're doing mostly Earth observation, Earth sciences, and we are a very fresh lab. We started just in September last year, was newly founded, and I said we're out in Earth observation using various sensors like from satellites, classical remote sensing over drones, which is this work, to also webcams, but we also use social media data and so on. The reason about various different things, using mostly machine learning, AI in general, and like many, since recently we've started to use deep learning, and we are mostly also interested in understanding what deep learning models are doing, and this includes explainable AI, so to be able to figure out why a model made a certain prediction or not. And something that is closer to my heart as well is we are working a lot on interactive learning, where humans and the machine work hand in hand, and it becomes kind of a feedback loop rather than having two disjoint sets of humans annotating and machines doing all the predictions. I'll talk about that in the end again. In terms of topics that we are following, one of them, a big one, is conservation, which again is kind of at the heart of my work and also what you're going to see today, mostly on wildlife like animals. But we also work on more traditional remote sensing topics like determining land use changes and so on. And in our lab, which is in the new cluster of the EPFL here in Switzerland, we are also to be studying alpine and Arctic data, like on the perception of Alps, or for also more physical topics like glacier melt. This is all going to come. We're going to dive into that too. And the people that work in the lab that I'm part of are these wonderful folks here. Well, the four on the left are in the new campus, in our new ECEO lab, which is, apart from myself, is Christelle Chapuis and Tianan Yen, who are two new PhD students. And of course, you might have heard of Davis Toya there in the middle, who is the head of the unit, is our professor. And the folks on the right are the ones from our previous university, which is Wageningen University in the middle of the Netherlands. And again, we have a couple of PhD students and a postdoc there, and we're closely working together still. And we're all working with many other universities and companies, including Microsoft, especially the AI for Earth team, the French CNES, NVIDIA, and also companies like Pictera and so on. So this is more or less a little bit about the ECEO team that I'm part of. And without further ado, let me jump into the topic of today, which, as Michael said, is on when a few clicks make all the difference in weakly supervised wildlife detection in unmanned aerial vehicle or drone images. And this is a research I've recently conducted, and it was part of my PhD on detecting wildlife using remote sensing. And the main question you might ask at this point is, why would you even want to do that? What's the point of trying to use a drone and detecting wildlife in the images they create? The motivation behind this is actually a context. Here's some statistics on the number of rhino poached, that means illegally killed, in Africa over the last few decades. There we go. Now, as you can see, in 2000 on the left, there were 6 officially registered rhinos that had been killed by poachers, and this number rose to a staggering 1,040 in 2017. So in just South Africa alone, the official number of killed rhinos has grown dramatically. And it's gone down a bit again, but it still continues to be a problem. Rhinos are being killed because of their horns. And if this continues, they're going to be extinct soon. For example, the black rhino last year was the number of black rhino left in the world was 5,050. And if you can imagine, in probably 5 to 10 years, if this continues, it will be gone forever. So what we need to do is we need to protect the environment. We need to protect these animals. But before we can even begin to think about that, we need to do censuses. in a repeated manner. We need to know how many animals there are and where they are. And especially wildlife reserves like the Kruger National Park, for example, they have been doing this over the last decades. And they have mostly been using drones recently, but before that also manned helicopters and camera traps, which trigger whenever an animal walks close by. Now, this is still a very established approach, but the problem is it's flawed. Because, for example, helicopters have manned people with binoculars. And so they're very imprecise because the estimated counts differ between the observers, and they're expensive, and they're very dangerous. Like, aircraft accidents are the #1 reason for deaths among ecologists in the field. And camera traps are also very imprecise because they can just monitor one particular location. So we might want to use drones instead, because drones provide you with high resolution aerial images. They are not so expensive, easy to deploy, and whenever a drone crashes, it's not a big deal because it will be harmed, and animals are not going to be harmed either. And people, conservationists, have indeed started to use drones for automated wildlife detection. And by automated, of course, I mean machine learning. And here's some recent results of that. The left one is one of mine, actually, where we use the drone and a deep neural network to detect animals. And we can see we're doing fairly well in terms of precision and recall. We're finding most of the animals, and we're not making too many mistakes. This is quite an improvement from what we had before. And on the right is another study, which has been conducted in Australia on detecting koalas. And they used all the drones, but thermal images. And also they found most of the animals, up to 100%, with a very high precision. So you can see it's possible to find the tiny animals in the images with deep learning and so on. So what's there to be done? What do we need to do still? Task solved, right? Well, not exactly. And here I'm referring to the introduction of Michael on that labeling can sometimes be very annoying, tedious, and expensive and difficult. And what I usually like to do at this point is to make a little bit of a quiz. So I'm going to show you an aerial image from a drone. And I'm going to tell you there's animals in there. And I'm going to give you a few seconds to figure out where they are. So let's start off with this one. So I'm telling you there's some animals in here, and I'm just going to give you a few seconds to try and find them. I don't know how interactive we can make this, so I suppose I'm just at some point going to give you the solution. I also don't know how well you can see this through Microsoft Teams, but just in case you might have spotted them already, if you look in the bottom left corner of the image, you will find that there's 2 ostriches. You can see that by the very distinct shape and by the shadow. So you can see they're kind of roundish with a long neck. Obviously, there's ostriches in here. These are not so difficult to spot. But now you know what to look out for. So let's raise the difficulty a little bit. Here's the second image. Again, I'm inviting you to take a few seconds and try and find the animals in here. Right, so at this point, you probably immediately notice the 6 animals in the middle of the image. These are probably oryx. But again, if you look more closely, you will find that there's actually an awful lot more animals in this image than these 6 in the middle. Some of them are hidden in the shadow. Some are at the edge of the image, at the borders. The thing is, I think you're starting to see that it is not so easy to actually find these animals in the first place, because you have to zoom in, you have to look very closely, and then you have to label them all one by one. It kind of takes a lot of iteration. But now, again, you know what you need to look out for. So let me show you the last image. And again, I'm inviting you to try and locate the animals in this shot. Make sure to look in the shadows of trees, to look at the edges of the image, I know you can't zoom in now, but it's also not needed. Just telling you, in case you have found something that looks like an animal in here, I have to disappoint you, because this image is void of animals. This is completely free of animals. And the reason why I'm showing you this is not to make a fool of you, not at all. Rather, it's to show you the scale of the problem, because this kind of images, the ones without any animals, are the majority. Most of the images you take with a drone over the tens of thousands of square kilometers in a national park are completely free of animals. And the problem is that going through all these images manually is, again, as I said, and as Michael said, very tedious. And this problem still is we rely on large hand-labeled set of images. If you want to train an automated deep learning-based detector, we need to label a lot of images with a lot of bounding boxes. Sometimes images contain over 40 animals, like here, many of them contain none. It's pretty annoying. So now we want to solve this. And with this, I'm going to start with a rhetorical question on what is easier. Let's say you get this image here, which contains animals, and you have to do one of the two tasks. A, you can draw a bounding box around each animal as precisely as possible. Or B, you just make one statement. This image contains one or more animals. And I guess from the context of this seminar, you probably agree with me that option B is much easier. It takes you a second to say yes or no. It takes you potentially minutes to draw boxes. And we want to leverage this circumstance. And so what we're going to do is, as Michael said, we're going to use weakly supervised object detection. And the idea here is we're going to go to the extremes. We want to provide image-wide labels, so just there's animals in their image or not, without any spatial supervision, and we want the model to figure out where the animals are, like in the image below. And that's exactly what we tried. So let me tell you a bit more about that. So the way this works is we get an image, we use a detector, could be a convolutional neural network in this case, and this detector doesn't give us bounding boxes, but what it does give us is a slightly lower resolution grid of a heat map, where basically every grid cell that is over an animal is expected to have a high value, close to 1, and every background cell is expected to be close to 0. And this way, this gives us spatial detections. And now the question is, how do we train this? Because we don't have any spatial ground truth. So what we do is, as said, we constrain this heat map to be scaled between values of 0 and 1. And then we design it in such a way that a heat map grid cell is more or less the size of a single animal. And then what we have is a one-to-one correspondence between the integral of the heat map and the number of animals present in the image. So we can simply, in reality, do a sum over all the grid cells and then compare to a ground truth. So our first ground truth, which we used for academic purposes, was to use counts. We assumed that we know how many animals there are in each image. So in this case, we compare this to the ground truth of 8 animals and backpropagate like in standard deep learning. And then, as a more realistic but also more difficult case, we went for binary labels. So where we just say, yes, this image contains 1 or more animals, or no, there is no animal at all in this image. So let me start off with the first one, the counts. This in principle is easy, you have a direct correspondence, but what we did is we used a so-called Huber loss, or also known as the smooth L1 loss, which basically is a conditional combination of an L1 and an L2 norm, of a mean absolute error and a mean squared error. So whenever the prediction, the integral, the heat map sum, is bigger than a threshold theta, we go for an L1 loss, a linear absolute loss. And whenever it is smaller than theta, we go for an L2 norm. We chose theta to be 1, so if the prediction difference and the ground truth is within one animal, we switch to an L2 norm. So the idea behind this is that it is very tolerant to outliers, because if the predictions are way off of the ground truth, the model doesn't get penalized all that much. And this is important because counts can be not very accurate. If you count very quickly in an image, you might not be super precise because you also want to get moving. So this is straightforward for our counts-based ground truth. Now, what about the binary case? Because in the binary case, we don't know, we cannot do that, because if the model predicts more than one, it could be true. We just know that there is an animal. So what we do is we again use a conditional loss, which is very simple. It says the loss is 0 if the ground truth says yes, there is an animal or more, and if the model predicts one or more animals. Basically, the model can predict an arbitrary number of animals, and if that isn't the case, we use the Huber loss again. So as said, this allows predictions to grow beyond 1, but now the question is, how do we make sure that our model doesn't predict, say, 7,000 animals each image, because the loss would always be 0 then? Well, the story is that we're training this on images that have animals and images that don't have any animals at all. We're using both. So the model cannot afford to always predict 700 animals. It has to differentiate, and it can only do so by figuring out what to pay attention for in the image, which in our case happens to be the animals. So much about the theory. Let's quickly evaluate this whole concept, see if it makes any sense. A little bit about the data source. What we're using is called the Kuzikus Dataset, which has been acquired over the Kuzikus Wildlife Reserve, which is a private-owned national park, a private-owned park in Namibia of about 110 square kilometers, and it is home to about 3,000 large mammals, mostly black rhino, ostriches, kudus, oryxes, zebras, etc. And we took an EB, a drone there, and acquired a number of images, and we split them up into different sets as usual. And we made sure to have these sets completely disjoint spatially so that we don't have any autocorrelation, and to also have them kind of balanced in the number of empty images and the number of animals. We did a bit more, a 60, 10, 30% split. So you can see this looks like we have a lot of animals, over 1,300, but if you think about it, 830 animals for training is not that much. And the number of images looks small, but these images are big. They're 4,000 by 3,000. So we crop patches out of them to train the model. And that's shown here. We crop patches of 512 by 512. And then we use a pretty lightweight standard model. I guess you're familiar with it. It's a ResNet 18, which usually does image classification. But in order to get a heat map, what we do is we remove the final fully connected classification layer, and we remove the average pooling. And we also reduce the stride a bit to increase the resolution. And then we take this remaining feature extractor, pre-trained on ImageNet, and we just add a couple of multi-layer perceptrons, or say actually one-by-one convolutions, to give us the heat map. And now another little detail. Now we have a model that predicts that, and we know how to train it. Now at test time, we also need to go a little bit of a separate route, because our heat map doesn't allow us to use classical metrics like intersection or reunion. So what we do is, first of all, we threshold it, say to everything above 0.1, which gives us a prediction like this. And then this often gives us neighboring activations around the animals. We want to get rid of those. So we use classical non-maximum suppression to only retain the position within a neighborhood that has the highest confidence. And now to evaluate this accuracy, what we do is, because we don't have bounding boxes, we use a distance-based validation, which basically is very simple. If we have a ground truth animal, we draw a circular radius around it of around 40 pixels, which is only 2.4 meters, about the size of an animal. And we say predictions are correct if they are within this range, and if there's no more than one prediction per animal. So we penalize double counts. Good. So now let's have a look at the results. Let me start off with a precision recall curve on the binary model. So this model has only seen yes, no ground truth. And we are evaluating spatial accuracy here. And as you can see, it actually finds almost 80% of the animals straight away in space. So it is able to localize the animals without ever having been taught where the animals are. It makes it has a high commission error, so the precision is relatively low, but still it's a lot better than what we used to get before deep learning, actually. If we increase the ground truth's semantics and include counts, we get a significant boost in precision and recall. So now the model can find almost 90% of the animals and makes less mistakes. This is to be expected because it gets more constrained to what the ground truth is. So far so good. Now, the eagle-eye viewers of you have seen in the title that we talked about this extra few clicks. Now, what is this about? It's very simple. Basically, what we do is we take a small subset of images, and for those we actually add spatial ground truth, which you can see on the right here. So, and this way we can directly train the model's output. We compare the heat map with the ground truth using a cross-entropy loss, and this gives the CNN a little bit of a spatial supervision signal. And we do this for a very low number of images. We chose 3 at random that have animals and inject spatial ground truth. And now if we do that with just 3 of these over 800 images, we suddenly get a massive improvement for both the binary and the counts model. So the binary model with these 3 spatially supervised images is in green, and the counts model with the spatial supervision is in red. And the interesting part about this counts model, especially the red one, is that if we compare it to our upper bound, a model that has been trained with always spatial supervision, it's actually even a little bit better. Now, this might sound a bit counterintuitive because we're decreasing the ground truth complexity, but we get a better result. But our hypothesis is that because we rasterize the ground truth into this grid, we hard code the location where the animals are supposed to be. But if we don't do that, if we just give count ground truth, we give the model an additional flexibility of shifting the points around so that it can learn better. But the long story short is that with just 1% of spatial ground truth and the rest for counts, we can get a result that is as good as a fully spatially supervised counterpart. It also has this 1% also has some other effects. You can see here, if we only use binary ground truth, we get big circular blobs around the animals, which gives a lot of false positives. And we can sharpen these, make them more crisp by adding a bit of spatial supervision, which you can see on the right. These models also make a little bit less errors. So in terms of absolute numbers, you can see in blue the binary only model, and in green, when we add a bit of spatial ground truth, you can see the number of predicted animals for each image stays a lot closer to the optimal line, which is the black dashed one, than in the binary case. So we have a lower count error overall. Right, so it works pretty well. The question is what still needs to be done. And there are some things which could be done, like this extra spatial supervision. We could think of more advanced heuristics. Now they're chosen at random. Maybe we can take model confidence as to which images to select for spatial supervision. And the question is also, where are the limits in weak supervision? Small 512 by 512. We want to use bigger ones because it gets even easier for humans, but we probably cannot use the full drone images because the animals are too small. So this might need a bit of an ablation study. Now, just very quickly, a summary. We've tried to come up with a model to detect animals in drone images, to protect them. And we try to do away with this tedious manual annotation of ground truth. And we found that it worked. So if we tell what instead of the where, it's enough to train a model or even outperform fully trained ones in such a setting, which is pretty cool. That's more or less what I wanted to show for the weak supervised labels. If I still have some minutes, I don't know, Michael, do I have some minutes left or?
Yes, go ahead. Yes.
Perfect. So I would also like to show a little bit of the most recent work I've been doing, which is a little bit related to that, but goes into a different direction. And it's about the task of labeling images themselves. And this is a collaboration between us and Wageningen and Microsoft AI for Earth. And the story is the following. I guess if you've ever labeled your own data sets, you know that you take these images, you have to label them. It takes a lot of time to be able to get to, like, for example, bounding boxes. And then you spend another large amount of time to train a machine learning model to do the automation on the rest. And the problem with this is not only time, the annotation becomes tedious. Like, at some point it becomes very monotonous. You start to make mistakes due to fatigue. And the machine learning model training is probably doesn't apply to you, but many people don't have expertise. They don't know how to code deep learning models. And so it doesn't even become tangible to them. And in this project, we wanted to solve both of these at once. And it's a software product called AIDE, which stands for Annotation Interface for Data-Driven Ecology, bit of a retrofitted name. But what it basically is it's a web labeling interface, which allows you to label various different types like image labels, points, bounding boxes, and pixel-wise segmentation masks. That instant segmentation will come, and it allows multiple users to label images at the same time through the web, through the internet, or through your local network. It's a web-based annotation interface in the first place, but what sets it apart from other such solutions is that it includes a full stack of machine learning and deep learning models in the background, and it does that using active learning. So basically, it has deep learning models in the background, which go through the large bulk of unlabeled images, and then they only show to the humans in order the images that are most interesting, like, for example, those where the model is most uncertain, or those that contain the highest number of detections, things like that. And then the humans can provide labels, corrections, which are in turn used to update the deep learning model in the background. So it really is a true feedback loop where humans and machines work hand in hand. And it has a plethora of functions already built in, like it has many AI models built in, including ResNet, UNet, RetinaNet, faster RCNN. It's all there, and all these models can be used without a single line of code. You can implement your own models if you have them. And it has some other nice features, like you can monitor progress, you can evaluate the accuracy of the users and the model in the web browser. It has very flexible data management. It is fully scalable, so it can run from your laptop to multiple cloud environments. It actually works very nicely in Microsoft Azure, which it has been developed for. I don't have time to talk about all of that. Just wanted to tell you that this is out there. It's in development. There's a paper on it too. And I'm inviting you to checking it out yourself, because it's on GitHub, it's completely free and open source top to bottom. And here's the link to that page if you're interested. And if you have more questions, of course, I'm happy to also provide you with answers. And for now, that's it. And I'm thanking you very much for listening, and I'm open for questions. Thank you.